Bem, bom dia a todos aqui e também remotamente. Good morning everyone that is present here and also remotely. I also will say bonjour à tous. But I'm sorry I can't speak French well, so I will not try it again. But I would like to say some words first about the kind of meeting that we are having today, because we have the LADES-GIMSCOP control seminars that they happen every fortnight on Mondays. But today we have a different presentation because it is going to be presential here. We have the honor of receiving here Professor Frédéric Marias from Université de Pau, Université de Pau et de Pays de l'Adour. And he is going to, his presentation is entitled, as you can see here, the activities related to dynamic modeling and optimization of multi-energy platforms that he develops at his lab. His graduate studies were at the Université de Pau, but he also spent some time later a period at the Imperial College in London, and he has many projects regarding energy, and so he will present about this research today. And also we have a collaboration with his university regarding exchange of students. Here in Brazil it is named Brafitec. It is an initiative from CAPES, and Professor Bruno and Professor Argimiro also participate. I participate too with the other universities from Brazil. So we are very glad to have you here. It's an honor, and thank you very much. I will pass the word to you, and at the end we can make the session for questions and comments, also from people that are watching remotely. So thank you very much.
Obrigado. Bom dia a todos. I'm sorry, but this is the only words I know in Portuguese, so I will continue in English. I'm very pleased to be there to give you this presentation. So the work I'm going to present is not only my work, but the work of all the team that we have in Laboratoire de Thermique, Énergétique et Procédés. This is Laboratory for Thermal Sciences, Energy and Process. And so this is the work also of Professor Jean-Michel Renaume, Associate Professor Sabine Sochard, and Associate Professor Sylvain Serra. The summary, so I will give a brief context of my university, where is my university, then some key number and information regarding my laboratory, and then I will present some activities that we have in the field of dynamic modeling and optimization of multi-energy systems. Because from my side, I'm more concerned with thermochemical reactors for conversion of biomass and waste. I will maybe speak a little bit more about this activity, but I will present the other one as well. At first, where is Pau? Pau is here. It's in the southwest of France, very near from Spain, very near from the Atlantic Ocean, from the other side, from here. And we have a castle because this used to be a place where we have a kingdom France, and we have, since we are very near from the Pyrenees, we've got beautiful landscape and beautiful beaches as well. Not as beautiful as Rio's one, but some beautiful one. Okay, so about my university. So since 2017, University of Pau won an important award for excellence. It's called an ICIT, and only 18 universities in France get this kind of award, so this is very important. We are the only small university, because we are only 15,000 students, that were able to win such an award, but because we have a very powerful research activities, because the headquarters of Total Energy Group are located in Pau. So with the researchers of the University of Pau, plus some of the researchers of the research center of Total, there are about 1,000 people that work within this energy and environment solutions ICIT. some important information is that in July, past July, the rector from the University of Rio de Janeiro went to Pau and to meet our rector. So there is a strong link between our two universities. And for the University of Pau, UFRJ is a strategic partner. So this means that with the aim of the LADES that I present you, we can have some grants to promote mobilities of researchers, of graduate students, and so on. So it can be convenient. And we were very pleased to welcome your rector in our university. Also, at University of Pau, we are member of an European university. By now, Europe is building the future of higher education institutions, and by now there are 41 European universities across Europe. Ours is called UNITA, and we have 6 universities, one in Portugal, which is Universidad de Beira Interior in Coia, University of Zaragoza in Spain, University of Pau, University of Chambéry in France as well, University of Torino in Italy, and University of Timișoara in Romania. This is an important university. We have at least we have a total 165,000 students and 13,000 researchers in this whole university. And we have 3 main topics: cultural heritage, circular economy, and renewable energy. And it's in perfect phase with what we are doing in our activity. Okay? And indeed, University of Pau is the leader for research activities within this European university. So, about my laboratory now. So, the head of the laboratory is Vincent Patel, with Deputy Director Sylvain Serra and Jean-Paul Serin. We are a small laboratory. We are only 22 lecturer researchers with 7 full professors and case associate or assistant professors. We have almost 25 PhD students and 10 master degree students. Dealing with the team in which I belong, this is the team for dynamic modeling and optimization of multi-energy systems. This is the 4 people that I spoke about at the beginning of my presentation. And we have almost 10 PhD students and 3 master degree students. Well, about our activities, so the core of our activity is steady state and transient modeling of and optimization of energy systems. So the skills that we need to have to do such research activity is at first to have basic on energy and process engineering. So of course, thermodynamics, heat and mass transfer, fluid mechanics, computational fluid dynamics, unit operations. We need also to have skills into optimization, linear programming, nonlinear programming, mixed integer nonlinear programming, and so on, dynamic optimizations, and recently dynamic real-time optimization, and also optimal control. Of course, we need some numerical analysis, so numerical methods, and we are still programming in Fortran. Maybe sometimes it sounds an old language, but we still use it, and also MATLAB and C++. And the systems on which we focus are heat networks, solar power plant, conversion devices, and reactor and industrial platform. So here is the scope, all of our activities. So we have here the primary energy sources: the sun, the wind, hydroelectricity, biomass, geothermy. And so we have all these primary sources that are renewable, and we need to convert them so that we can produce electricity, which is going to be into the grid, produce gas that is going to be circulated in a gas network, and to produce heat and cold that are going to be delivered to in habitations through pipes and networks. So we are speaking here, for example, about conversion. So biomass can be converted into gas using anaerobic digestion, using gasification. when you make the anaerobic digestion, you produce, of course, some methane, but also some CO2. So if you add hydrogen, for example, to this carbon dioxide, you can handle the Sabatier reaction and then produce methane. And to produce the hydrogen, well, you can have solar panels that will produce electricity, then that will go to an electrolyzer, and then that is going to feed the hydrogen. So we built some mathematical model of these units, and then our goal is how can we make them work together in the most efficient way. I mean, for example, regarding the demand on heat or on gas, regarding the weather forecast, regarding the sun, how it shines, what is the operation that we should run? Should we put into operation, for example, the catalytic Sabatier reactor or not, or store? This is all of this. We want to try to make the optimization of such operation. So at first I will, because as I mentioned at the beginning, I'm more focused on chemical transformation. So an important part of the activity deals with the modeling of reactor for thermochemical conversion of waste and biomass. So we are speaking about pyrolysis, combustion, gasification, gas upgrading. How do we work? We are setting up some specific models to represent the operation of complex reactors, like fluidized bed, rotary kiln, fixed beds. And we are building some steady state and transient model. So at first, an historical study that deals with fluidized bed incineration of sewage sludge. Indeed, this is an historical study because this was the subject of my thesis that took place some years ago. And then here we've got an industrial fluidized bed reactor for incineration of sludge. And as a partner with Veolia company, we build a mathematical model. So we rely at first on Levenspiel work on fluidized bed. Then we consider that the bed was a bubbling one. So we build an assembly of reactor. The bubbles circulate as a plug flow. We have a CSTR here for the other part of the gas and two plug flow reactors for the freeboard of the reactor. And then using this kind of assembly of ideal reactors that we all know when we are doing some chemical engineering, we were able to understand how was operated the incineration of sludge within the reactor. So for example, here you've got a picture of the oxygen level within the reactor. So most of the oxygen cross the bed in bubbles, while the pyrolysis of the sludge take part into the dense bed here. Okay, so we have here the release of carbon monoxide, which is a tracer for where the pyrolysis take place. And so the combustion of the volatiles of the sludge take place at the interface between the bubble and the dense phase. At the end, here I present a comparison of the results of our model for the production of nitrous oxide, which is an important pollutant when you deal with fluidized bed incineration of sludge. And what is very interesting is that this is a comparison that were obtained from this industrial reactor. This is a reactor that is daily operated at the industry scale. And we can see that we have a very good agreement, except in two cases. And we think that we have this discrepancy here because as it is an industrial reactor, it is not always easy to get steady state. And if we are not a steady state, we cannot properly predict the estimation of nitrous oxide. Another activity, so with this first model, we build a real-time simulator for fluidized bed incineration. This kind of tool is used for the training of the operators. Okay, by now, when Technip, for example, build some refinery for Qatar, for Saudi Arabia, or I don't know where, they also provide a real-time simulator for the training of the operators, because it's very convenient that you have a twin, numerical twin of the plant. So we did it for this fluidized bed incineration of sewage sludge. Another activity that we have is indeed linked to the pyrolysis of waste and biomass. Indeed, as we are building some mathematical models, the first step is the reaction pathway of pyrolysis. What happens when you heat a solid? Okay, so classically, we do it in a TGA for the thermal analysis. But in the TGA, you can only have samples of 2 to 5 milligrams. And it's so few when you are dealing with waste. It's not relevant. So we have built this tool, which is a big TGA, which can hold up to 1 kilogram of waste here. And it is exactly the same as a classical TGA, except that we have a big load here of waste that we can put inside. And you've got this furnace, we can control the heating rate, and we recover, you don't see it here, but we recover the produce of the pyrolysis. Okay? We recover the condensable part, which are the primary tars, and we recover the permanent gases. Okay, and for this, we have built a 2D in space mathematical model of what happened inside the basket. So it's 2D in space and transient. So you can see here, for example, the evolution with respect to time of the temperature inside the basket. So here, at first it's cold. Then you feed here with some hot air that comes from the bottom. So you can see here that first we heat by the bottom. And as far as the moisture content is not completely evaporated, the temperature does not raise too much. And then you've got the pyrolysis and then the cooling. And so if we look at the mass loss as a function of time, this mass loss with the dot corresponds to the experimental one, which is continuously measured, because here we've got a balance which is cooled and which allows for the weighting of the basket. And so we see that we have excellent agreement between the model and the experiment set. Another activity now is a collaboration that we have with Marco Castaldi in City College of New York and University di Bolzano, the Free Bolzano in Italy. So still we focus here on the pyrolysis and on the primary pyrolysis. So the system that we have is here, for example, a sphere of wood. We locate here a thermocouple and a probe. And this probe is linked to a gaseous chromatography that will, every, I don't remember, 3 minutes, pump inside the wood particle to extract the gas that are produced and to have information on the primary products. So I don't know if it will work. We have built the model of what happened inside the particle. So you can see here on the horizontal scale, this is the radius of the particle. So here is the center, and here is the external surface. You've got here the temperature, here the moisture content, here, don't remember, the internal pressure, here the composition of the gas, here the conversion, and here the mass of the sphere. And you can see that we are able to, indeed our problem was that with the pump of the chromatography was not efficient enough to pump inside the system because the permeability of the wood was very low, and so we did not understand very well at the beginning. And so we built this kind of, okay, you see here, so here we are not pumping, and then we began to pump. So the pressure here collapsed because we are pumping, and so is the moisture content there because the water is extracted from the particle by the chromatography pump. And then, so if we can go forward that way and see, oops. Well, it's not, I can't do it as I would like to do. Okay. Okay, so, but we are able to predict. Okay, I should have done this. well, we are able to predict now the pyrolysis process because now the temperature, here you've got the set point of the external heater, so the temperature raised at the surface of the particle. So you begin to see that here the pyrolysis has started because you can see that the fresh wood has been transformed, and so we begin to see the char and we begin to see the tar formation. And so we are able to capture the exact information of what happened inside the particle. This is, to some extent, very, this is very, not fundamental information, of course not, but it can sound to be very, very detailed. But indeed, when you speak about combustion, gasification, this is the first step that you need to really understand. How does the solid material is converted into gas? Okay, so next. Okay, we also work on the thermal cracking of tars. When you deal with gasification, the main drawback for gasification is that you are producing heavy tars, like naphthalene, like benzene, like toluene. And so with a company which is called Europlasma, okay, it was, they built a process, a gasification process with a gasifier and a high temperature unit to crack the tars that were produced during gasification. And the main characteristic of this reactor is that the high temperature is reached thanks to a plasma torch. Okay? So we started from almost nothing. We start from a literature review to understand what are the tars that were produced. And so we begin to think about 4 model compounds, which were phenol, naphthalene, toluene, and benzene. And then we, thanks to literature, we built the reaction pathway that can explain the degradation of tars through methane, through soot, through acetylene, and then at the end, the transformation of tars into carbon monoxide and hydrogen. What is interesting in thermal cracking the tars is that you keep the lower heating value. So we start from there. We build a CFD analysis of possible configuration of reactors. Okay, with Europlasma, we have tried a lot and a lot. And then, at the end, we were able to draw this kind of graph, which shows for each of the spaces that are involved in the reaction pathway, which is the reaction, I'm sorry because it's very small, which is the reaction that leads to the main transformation. So for example, here, I think that this is the concentration of oxygen, and it's mainly consumed by carbon monoxide. Here, you've got the particles of char that are produced, and they are mainly consumed by dry reforming and water and steam reforming. So we were able to capture all the information to understand how we could have a better design of the reactor, and finally, the plant was built. And so it's still in operation. Dealing still with Europlasma, we built the model for the gasifier. So this model for the gasifier was a coupling between an homemade model based on 1D analysis, okay, and a CFD model of the gaseous phase, which is here. Indeed, the homemade model received from the CFD model the heat flux that comes from the radiation of the flame that you have here. And then, thanks to this heat flux, the model is able to compute the evolution of the temperature along the bed, which is the boundary condition for the CFD analysis. And the homemade model is also able to compute the composition and the mass flow rate of volatiles that are released into the freeboard of the reactor. And so you have the coupling. And then you are able to understand how the gasification is operated. And just here, you've got this reactor. Okay, it's in the wrong order. I'm sorry about this. Okay, so we have also worked on the Sabatier's reaction. Sabatier's reaction is the addition of hydrogen on carbon dioxide. An important characteristic of this reaction is that it's highly exothermic, and so it needs that the reactor is cooled. Okay, so we have a reactor with a classical shell tube reactor. We have a catalyst inside the tubes here, and we have some oil that cool the reactor to avoid the runaway. So we build a mathematical model based on pseudo-homogeneous reaction, 1D assumption, and here I show you, here it's the position along the reactor, so the reactor is 1 meter long, the tubes are 1 meter long. Here you've got the temperature, the set point for the oil, you will see the temperature of the gas and of the oil. You've got here the flow rate of gas, and here the composition. So at the beginning, the reactor is completely completely full of hydrogen. Then we have increased the set point of the oil, so the temperature of the oil and of the gas, okay, increases. You've got here the time, so I can maybe accelerate. I will try. And then once the reactor has reached the desired temperature, we begin to introduce the carbon dioxide. So now we've got a nominal flow rate at the input, and we've got hydrogen and carbon monoxide that are in stoichiometric conditions. And so as the operation process, we have the production of water and methane. So everything goes well, and we almost reach a steady state. Now I will show you something which is very problematic indeed. I will try. So we are going to go to 3,000 seconds. I'm almost there. Okay, and you will see that here, you see, during 10 seconds, we increase the temperature of the incoming gas of 10 degrees during 10 seconds. And what happened? You have a reactor runaway. Only because we have increased the temperature of the incoming gas of 10 degrees during 10 seconds. So this reactor is very subject to runaway. So we have built this model. We have tried to understand how such possibility could be avoided. And we have integrated this into a dynamic optimization algorithm in order to decide what should be the best concentration of catalyst inside the reactor, how should we stage the catalyst concentration inside the reactor, so that we never get this kind of runaway, with the objective function to have a nominal yield of methane. Okay. Now another subject on which we are working now is about the treatment of microalgae. So microalgae and invasive algae, indeed, for example, in Brittany, there is a lot of, I don't remember the name for raising animals, and this makes a lot of pollutants inside deep water, which finally goes to the sea. And so there are a huge amount of algae on the beach in Brittany at some period. So how to treat this biomass? So the idea is that we can have some pre-treatment like acid washing, drying, wet torrefaction, dry torrefaction, and then combustion, gasification, and further valorization as methane. Here what we are doing is an ME and LP analysis, because we are trying to find out what is the best layout of all this unit operation regarding the composition of the incoming waste and regarding the final product that we want. Do we want some heat? Do we want some hydrogen? Do we want some electricity? And depending on what we want, our model and optimization algorithm will define the structure of the process that is optimal regarding the economics of the process. Okay, we have also worked on electrolysis. Okay, because electrolysis is a process by which water is converted into hydrogen and oxygen. So we build a mathematical model. The mathematical model is mainly built on the modeling of the stack, where the electrochemical reaction takes place. And then you've got two separators, one for the oxygen and one for the hydrogen. We have built the mathematical model of this, the dynamic mathematical model, and then we have used it to try to optimize how should be operated the electrolyzer. Indeed, here is the price of the electricity in France in 2019. You've got the 12 months, so you can see the fluctuations in the price. And we wanted to reach a production of hydrogen. I don't remember. I think it was 100 kilograms. I don't remember. Sorry, but this is not that important. But using our model and algorithm, we were able to define when should be operated the electrolyzer regarding the fluctuation of the price. And if we do this, if we use the electrolyzer that way, we have a decrease of 17% of the price of production for hydrogen. Okay, so this is typically the kind of model that we are building. Okay, we are also working on the absorption machine, because when you speak about heat networks, okay, there is heat networks. The heat is produced, for example, by a biomass plant, which produce the heat. But then biomass plant cannot be shut down and shut on as we would like to do, okay? So we need to store the energy when there is no demand. And so some possible activity about storage of the energy could be by adsorption, meaning when we have, for example, some zeolites, and if we adsorb some water on zeolite, we release the heat, while if we desorb, we store the heat. Okay? So it's a convenient way, and we have built dynamic model to understand how heat could be stored and restored to the network. Now, some important work that we are doing. I'm no more on the field of conversion, but on the field of solar power plants. So in some past work, we have performed some dynamic optimization of solar power plant. So typical solar power plant is that one. We've got a solar field where we have some solar panels that convert the sun irradiation into heat. This heat circulates into some pipes. Thanks to a heat exchanger, the heat can be stored and then finally delivered to some consumer. Okay? So the first step was the mixed integer dynamic optimization of this kind of unit. I mean, we know the weather forecast and we know the demand. And so our algorithm produce the mass flow rate, compute the mass flow rate of water that should flow into the solar panel, that should flow into the storage tank, and so on. So this is a dynamic optimization problem, and our optimization variables are the mass flow rate of water that circulates in all the system. So we had this optimization, but then our present work deals with dynamic real-time optimization. Indeed, as I mentioned, the operation of the plant is driven by the weather forecast and the forecast for demand. But weather forecasts are not 100% sure. So there might be deviations from the weather forecast. And if we have such deviation, how do we do? Because what we have computed as optimal is no more optimal. So to do so, we use dynamic real-time optimization. Okay? And we are working on this with Professor Gallo, Carrillo-Leroux at USP, that you know. Okay, we are also working on heat networks, heat and cold networks. So we had some past activities on how to design the structure of the network. So this was a MENLP algorithm. I mean, for example, we've got production here, another production here of heat. So how should we design the network so that its cost is the lower one? Okay? So how many pipes, what is the diameter of the pipes, and so on. We had this analysis for heat network, and then we go to a second type of unit, which is this time a cooling network. So we have several kind of units that are connected to this structure, which are production, habitations, malls, and so on. And we have the pipes that connect all these, I don't know, operation together. So we design a superstructure, and then the dynamic optimization algorithm was used to compute the structure, the diameter of the pipes, and also regarding, for example, here, if we finally have this network, regarding the demand that we have here, that corresponds to the demand in, for example, in habitation, in malls, and so on, we are able to compute the mass flow rate in every pipe. Those are our optimization variables, and those are the results of the computation. And you can see here that we have made the simulation with insulated pipes and non-insulated pipes. Okay? So this is the result of the computation. Is that one is the optimization variables, the mass flow rate that circulate inside the network. Okay, so now what I've shown you is that we have built model for this, we have built model for this, we have built model for this, we have built model for storage as well, and for absorption. But now, what we need to do, our aim, is to put all these things together. And so now we are working on several coupling. Coupling electrolysis with a methanation reactor and with anaerobic digestion. Okay, because the three will need to work together. He did it in my city, in Pau. There is a plant that is going to be built on the wastewater treatment plant. This sludge is going to be connected, put into an anaerobic digester, and then it will be connected to a Sabatier reactor and coupled with an electrolyzer. So we are building the connection between all our models to be able to represent such a unit. Okay? And our aim is to build all of this. This is ambitious. Okay, at present time, what are we working on? So we are working on a very important field on which we are working now is the dynamic optimization of multi-energy systems. And we want to do real-time optimization and connect this with big data. So at present time, we've got a program which is called Impulse. Impulse is a program with an industrial which owns a gas network in southwest of France and which work on the same topic. And we are starting a work, very important for us, and maybe we can find some connection, which is called Réseau Data, because we are going to work on a heat network which is located in Bordeaux. This heat network has a lot of sensors, very important amount of sensors that in real time give us the information on the mass flow rate and temperature. And we would like to use artificial intelligence, neural networks, to build a black box model on which we will apply real-time dynamic optimization. Okay? That's one project that we are going to start now. We are also building some new unit operations because at present time we do not have any model for anaerobic digestion, and we are enhancing our models for gasification units because we've got the one for the great furnace, but we would like to have a model for entrain flow reactor for gasification. So we are working on this as well. And we have our final goal is to have a kind of platform where all these units are grouped together. We have some models, for example, for gasification in Fortran. The anaerobic digestion has been done in Python. The model for the heat networks has been done using orthogonal collocation on finite elements in GAMS. So we have plenty of tools, but then, okay, how can we make them work together? So we want to build some kind of platform, dynamic platform, where we are going to be able to connect together all these units. Okay, here is our collaboration. So we've got important collaboration with USP and also with EPFL, François Maréchal in Lausanne. With the Research Council of Norway, with the University of Louvain, École de Technologie Supérieure in Canada and Montréal, the European University, some partnership with French laboratories, Laboratoire de Génie Chimique in Toulouse that you probably know because this is also a member of our Graphitech program. And we have also some important collaboration with companies like CA, Total, and so on, and also with institutional partners in France. Okay, well, I think that's it. Thank you very much for your attention and for listening to me. I don't know about the time, if I'm okay or not. Thank you very much. And I'll be pleased to answer any question if you have.
So now if you have questions, you can address the questions. And also for the audience that is attending remotely, you can send your questions and comments by the chat, and I will read it for Professor Frédéric. Okay, I will ask the, okay. So thank you very much for your presentation. I think it is, you have shown from the design of units for energy systems, in the integration and the modeling and operation, optimization, and you see many of us work with different aspects like optimization, for example, artificial intelligence. And so maybe in the future, that slide that you showed, our group could be there cooperating with you.
This is something that maybe we can discuss.
Yes, thank you. And I suppose that this subject is important in terms of the energy transition, but I suppose that presently with the situation of the war in Ukraine and maybe the winter coming, if these processes are even more, you see, privileged, people are giving more support for that. And then, I don't know if you can say something about this later. Yes, and or we can start with the questions from the audience. Ajimiro has one. Oh, okay. So, for the audience, you don't need to type. You can open your microphone, pode abrir o microfone e fazer a pergunta direto, ok? Pessoal, em inglês, tá ok? Então, so, but you have raised your hand, so I will pass to Ajimiro. Thank you.
Thank you very much. Ajimiro?
Another microphone, I think.
Well, we can do it that way.
Okay. Well, it was a very nice presentation. A lot of work that you are doing there, your group, research group, and regarding this renewable system, energy system, all this integration and from biomass, from solar energy, and many things that you have done regarding modeling, dynamic modeling, optimization, for process design, for process real-time optimization. So there's a lot of process system engineering work that you are doing there. That's very nice. And this, there are a lot of things in common that you are doing here and there. So have a very high potential of collaboration. And I say I have the answer for your last challenge, how to put all these things together. Because you already developed a dynamic simulator, equation-oriented dynamic simulator, that we are developing since the 20s, 2001 and so on. It's more than 20 years of development of this simulator. And then you can bring all these models, it's very simple, inside of that and do all this integration that you need. I think we can work together on this to put everything together now. Yeah, that's...
Indeed, we are looking for such a solution.
Yeah, so...
we are very open to
that's...
any advice or collaboration.
Yeah. But right now, for example, you have some students working in the modeling, dynamic modeling of the anaerobic gesture from the biomass gasification, and you have already some work in pyrolysis. Some of these models already written. Yeah, and some others that you have, you can translate from Fortran to this model language. It's a very simple model language to translate there. You have solvers, for example, finite orthogonal collocation and finite element inside of that you can use for those solutions that you have applied. Many of plant scenes that you can do some.
Like yes.
Yeah, I think you can think about that.
Thank you. Thank you.
And can you talk a little bit about this modeling part? How deep you go in these model equations? And for example, you show us the CFD with simulation. They use some software for CFD, or you wrote your own model equation?
For CFD, indeed, we use ANSYS Fluent.
Oh, Fluent. Okay.
Because I've been start using it in 1994 during my master research internship. So I know it quite well, so it's quite convenient. Because this is a very important tool, difficult to understand at the beginning, so I use it because I know it well. What we have dealing with the tar cracking model that we have done, the real added value is that we have some specific properties because of plasma. For example, the heat capacities of the plasma gas is very, very different from the classical gas, and we introduced all the reaction pathway. Mm-hmm. This is what we did, but for the rest, we use all turbulence model, radiation model of the CFD. For example, when we deal with the Sabatier catalytic reactor, we write everything by ourselves. So we start from scratch, and we derive the mass, energy, and species balance with some assumption. For example, it's a pseudo-homogeneous model that we used in that case. And then we use the method of line to transform the partial derivative in space into algebraic one. And then we use integrators like DSSL or gear algorithm to solve the problem, which is stiff. Mm-hmm. So this is the reason why we use such model. For the network, for example, the cold network, we have models for the pipes because we are computing the heat losses. So we have 1D model in space and integration in time. And in that case, we use orthogonal collocation and finite elements for both space and time, for both direction. Well, we most of the time, and this is a main drawback, we're starting from scratch. Yeah. we use at least we use some algorithm. For example, for the gear method, we are using the DSSL with sparse matrix. Mm-hmm. But we did the analytical Jacobian work by ourselves, which is very awful. Indeed, yeah.
Just in order to do this symbolically and automatically.
and it helps winning a lot of time for computations. Yeah, the one you can do. Otherwise, you can't do optimization if you do not have this step.
One question is more regarding the curiosity is in your Pau city, how this integration between all these plants could be carried out in this integration, because you have your utopian plan it's to do all this integration between the solar energy to the methanation and so on. Is that possible to do with these different companies, integration, do this energy integration and mass integration?
Indeed, I mentioned a project which is called Impulse 2025, and this is a collaboration that we have also with François Maréchal in Lausanne. So his part of the work of his team is to design the steady state plant. Okay. Should we have a storage or not? Should we have the electrolyzer or not? And once it has been designed, we use dynamic optimization to define the operating conditions. Mm-hmm. We're defining the set points of the regulators in this, of the control loops.
Yeah, but I mean that there are different companies running all these units.
In that,
not the same company.
In that case, this is the same company. This is Terega. Because this company, they do not own, because I think it's the gas network, which is in all the southwest of France, that deliver the gas to the companies, to the levers. I don't think they own it, but they exploit it. And so they want to, because they have the possibility to distribute the gas and to accept the gas that might be provided to the network. Mm-hmm. So they're very interested in this kind of study. And this is the reason why we had this project with them. Okay. But this is only a single company there.
All right. Okay. That's no problem.
About the other project that I mentioned with the wastewater treatment plant, the anaerobic digester, the catalytic reactor, this one is with the city of Pau, because they own the wastewater treatment plant, and they have asked, I guess this is Suez company, to build the plant, to exploit the plant, but we have collaboration with the city.
Okay. All right. Mauricio, any more questions?
Next one is Professor Paul.
Thank you for all the information about energy initiative for universities. I have some clarifications from you. You mentioned about the pellet model. You had a wooden pellet, spherical wooden pellet, and you put many sensors in it.
Yes.
And try to see the dynamics of gasification. How do you take diffusion and reaction into account? Is reaction really important in that, or only diffusion is the problem? The wooden pellet must be.
For the wood pellets, indeed, we take into account heat and mass transfer inside the particle, and thanks to overpressure. So this means that if we are overpressure, we've got with the Darcy's law some velocity that drives the gas that are produced out of the particles, and we also take into account diffusion of such spaces, okay, with effective coefficients. And for the reaction, this is precisely what we want to do, is to determine the reaction where on the left side we have wood, and then on the right side we have char plus volatiles, and these volatiles have a condensable part and a permanent part. And we are working on what is this reaction. But from the engineering point of view, for example, you've got the team of Ronzi in Politecnico di Milano, who has established a very important reaction pathway to describe cellulose, lignocellulose, and lignin reaction, pyrolysis. But such models are very, very heavy, very, very complicated, and you can't put this into a gasification reactor where you will have hundreds of particles of that kind. So we are trying to be pragmatic and to have an engineering approach to build a single-step reaction model, but that for which we are able to validate the fact that it corresponds to the product that we extract from the particle. I don't know if I answered properly your question.
No, how much you can separate diffusion from reaction in such a case? Maybe
we compute both. We compute both. As the solid, for example, is transformed.
Can you measure diffusion separately or reaction separately, reaction rate? No.
This is modeling, so we can shut down diffusion, we can shut down reaction, and so we can see which is the most important phenomena. And indeed, the most important one is that as you convert the solid into gas, there is overpressure, because there is a volumic expansion, so it leads to overpressure, and this overpressure, thanks to Darcy's law, linked to velocity of the gas outside the particle. And this is the main phenomenon.
So because we're wondering about pore networks inside that, maybe porous network. It is a porous substance, right?
Yeah, that's a porous material, yeah.
The other thing is about a general question. You talked about integrating various energy platforms and this and that. There is a question of speed and scaling, right?
Yes.
Because there's a time frame for all this. Maybe they want in 1930 or 2030 or something. Do you really think it's possible to integrate all this with the speed and scale up your laboratory work at the national network scale?
Well, so all we do is numerical work, so we can upscale as we want. The size that we want. But, for example, when we deal with the anaerobic digester and the electrolyzer, it corresponds to the plant that is being built in the city of Pau. So we are applying our models to something that exists. Okay? Dealing with the time scale, you're absolutely right. For example, the time scale for anaerobic digestion is very different than the time scale for the Sabatier's reactor. We are speaking of 4 to 5 days for the anaerobic digester, while we are seeking for 10 seconds in the Sabatier reactor. So we have to handle this into the optimization algorithm.
The other is your opinion, perhaps not related to your talk. Now you see that every country wants to have energy initiative. You go to the US, say MIT has energy initiative, Stanford has energy initiative. Everybody says energy initiative. Everybody says now green technology, climate control, right?
Yes.
And it has even become a policy of the NSF and presidential level and strategy.
Okay.
How serious is France about turning to green technology?
Well, in France, we have a very important nuclear production of electricity. So it changed a lot about the policy of France. But by now, with the crisis that Mauricio was mentioning with Ukraine, we have no more gas incomes. So there is important policies to support, for example, anaerobic digestion, to support solar panels. At present time, there are a very important amount of money that the government give to projects to increase the renewable part. There are some scenarios of the International Energy Agency that says that in 2070, we should no more emit any carbon dioxide. No more. The only one that we produce, because we will still need some fossil fuel, but we have to store the carbon dioxide that we produce. So that in 2070, no more carbon dioxide is released to the atmosphere. That's one possible scenario. There are many. But I think it's a good objective, even if it sounds very far. But we need to go in that direction.
Do the government really finance your projects towards this end? Or?
For example, we have support for our modeling from the city of Pau. We have support from some companies. We have, it depends, we have various funding sources. And since we are in the university, in the academic, the government supports our salary.
Okay. The final question. In your first diagram, you were showing various parts, the whole integration of energy multi-platform.
Yes.
The left-hand side was the hydrogen thing. I saw
yes.
that electrolysis.
Yes.
Showing that. Which technology you really prefer? It's a blue hydrogen, green hydrogen, or gray
The
or
one,
white.
there are many colors.
So
In
how
France,
to try to-
in France, for example, we can produce hydrogen from electrolysis using,
people don't think that is not energy efficient. For
using,
example.
using nuclear plants. So it's great. Our aim is to move towards completely green, meaning we are solar panels that produce electricity, that goes to the electrolyzer, and finally that produce hydrogen. The efficiency is awfully low, that's right. But we produce that way hydrogen without any byproducts. But we need to think about the life cycle assessment of such process because we need to produce the solar panels. And what do they become when they are finished? So indeed, we can think, oh, everything is renewable, this is fantastic. But to my opinion, and this is also some direction that maybe we should think about, is life cycle assessment. Because this should be the only objective function of our optimization algorithm. But this is a huge amount of work to do.
The last question, do you think hydrogen, sulfur dioxide are raw material or you think as a fuel?
Hydrogen as a
Commercial hydrogen, for example.
In the city of Pau, we have buses that are fueled with hydrogen. So it's a convenient fuel. It releases only steam. I don't know if I get your question. Was it your question?
Not really. For example, 100 years ago, there's a Haber process. There's no way to beat that process for thermodynamic efficiency anymore. It's not possible. Nitrogen and hydrogen, the final ammonium nitrate or some fertilizer.
Yes.
Thermodynamic efficiency is almost 99% of Haber process. So how do you invent a new process for using hydrogen as a raw material from these sources? It's not very clear to me.
Well, there are probably plenty of possibilities. For example, if we have carbon monoxide plus hydrogen, we can build almost any chemical compound with these two components. Carbon monoxide plus hydrogen. We can build everything. Fuel, for example, using the Fischer-Tropsch synthesis. You can build methanol, you can build methane, and even more complex compounds.
So you see that Carnot Institute, the thermodynamic efficiency make any sense in this? That's
yes,
what I want to know.
of course.
Can you do better than a leaf, for example, the plant next door? That's all I want to know.
I'm not sure we can do better than nature. I'm not sure we can.
No, any question from the audience here? Because, people that are attending remotely, I will just say one message here that came that I think that summarizes the general impression. And I don't know if you remember yesterday you met José Torraca, one student that presented the crystallization unit. So he wrote for you a comment en français. So I will try to read it. Of course, it will not be completely right. He said, merci pour la présentation, professeur. Il était très bonnet et la qualité de la transmission aussi. So thank you very much, and
merci,
I think yes, and also other ones said in English the same comments. So thank you very much, and thank you everyone. Ajimiro has another comment.
Question regarding to the one of your examples that you show, the combustion of sludge. You used the Levin-Spill model for fluidized bed. I think it was in your thesis.
Yeah, some time ago.
Yeah, but I quite not understood that picture that you have shown with the.
Can we come back to the switch?
Yeah, was regard to the temperature distribution and concentration conversion distribution. Because when you use the Levin-Spill model, They are a compartmental model. No? You have the bubble
Here.
phase, this one.
That's one.
You have the dense phase, the bubble phase, the disengagement phase. So
Yes.
all these phases.
Yes.
But the bubble phase and the dense phase, they are just an idealization of those fluidized beds. It's not physically separated.
No, they are not physically separated.
But when you show this picture in their distribution, seems that you are presenting this separation.
Yes. This is a way to present the results. You're absolutely right. Indeed, the bubble phase is not continuous. We have represented as a plug flow reactor, but this is not a continuous phase, for sure.
Yeah.
But this is a way to represent, to some extent, how our model works.
Looks like that you are putting especially the temperature and in this case is the concentration of oxygen and
here
CO.
this is oxygen and here this is carbon monoxide.
That is more concentrated in the middle of the fluidized bed, but these are the regions. These are ideal regions, not the space of your reactor.
No. It corresponds indeed to that view.
This idealization, not the real space of the reactor. Yeah?
No, absolutely. This is only the way to represent what computes our model, given this very particular representation.
Okay. Then when you compare to the experimental result as only the output of the process, you cannot have measure.
We don't have any sensors inside.
Yeah,
the sensors at the output for the temperature and for the flue gas because they are controlled by environmental regulation.
Mm-hmm.
So we have only information about what happened at the end. But since we are speaking of very low concentration, this is in milligram per cubic normal metr cube, so this is very low. It's 100. So we think that if we are able to have such good fit with the experimental value, this means that maybe what we have inside is good, but we have not.
I know this 11 spill model for a fluidized bed is quite nice model. It's a simple and very well representative.
It's based on the work of Werner, the two-phase model, but with the assumption that around the bubble you've got a film. Okay, this is not the Kuhn-Levenspiel model. This is the Werther model. Sorry, not Werner. Werther. So two-phase. Dense bed with two-phase, bubble and emulsion, plus a film surrounding the bubbles. And indeed, it was very convenient for such model because the oxygen flows across the bubble. Okay, so this part is rich in oxygen, and here, this is where you feed the waste, the sludge. And because of the sand, because it's hot, this is the region where the pyrolysis occurs. So there is a flow, because this is there is more gas now than the incipient fluidization gas. So there is a flow of volatiles that goes toward the bubbles, and so in that film, this is where the combustion proceeds.
Yeah, sure.
And so this is what we see here. Okay, you can see here how the oxygen collapse, and how here you've got this, in this zone, high amount of carbon monoxide, and here you can see exactly the extent of reaction. So this is a representation, for sure.
No, but that's quite nice.
What sludge is you're talking about? What sludge is it?
I think this is secondary sludge from wastewater treatment. Secondary sludge from wastewater treatment. This is bacteria, almost microgranules.
Okay. Okay. You see the audience restarted. So please.
Since we went back to the slides, what the pyrolysis with the RTO? No, sorry.
The RTO.
Oh, with the electrolysis. Sorry. I heard pyrolysis. Sorry.
Yes,
Yeah, this one.
Do you also, how can I say, evaluate shutdown? Because I see there is moments there is a production is almost nothing.
Yeah, yeah. Sometimes when the price is very hot, very high, sorry, the electrolyzer is shut down. This is an alkaline electrolyzer type, so it can be almost easily shut down and shut on. This is not a high temperature electrolyzer for which it would be different, but for us this means that we would have constraints.
Because I was thinking, did you shut down the plants sometimes?
Sorry?
No, I was thinking that sometimes you had to shut down the plants if the price got low.
Yes.
Yeah, that's the case. Here it's shut down. Here it is not operated here. When the price is very hot, it's very high, sorry. It should be winter. The price, because in France, most of electricity is consumed during winter when you have a lot of heating devices that are operated inside habitations.
Here's summer because
Yeah, it would be so your summer is our winter, so maybe we could have the same curve.
Okay, so I also invite the professors and the students that are here. We are going to have lunch, then you can come with us and keep on talking. Okay. You are invited. And, but I would like to say again, thank you very much, merci beaucoup, and thank the audience here and people that are watching home. Thank you all, and see you in our next seminar. Yes, this presentation has been recorded, and we will make it available later in our site. And also, I will send it to you so that you can. Yes, thank you very much.
Obrigado. Muito obrigado.
Muito obrigado. Merci beaucoup. Thank you all. See you next time. Bye bye.
Bye. Thank you.
So I will end it here.